Okay, let's get started. So last class, we introduced the concept of an induction motor, and we also finalized the equivalent circuit of an induction motor, which essentially is exactly like a transformer, except the secondary winding is short-circuited. Okay, that's the major difference between a transformer and a motor. All the power is going to be sent to the rotor circuit, which is going to get converted to mechanical energy. So our resistor in here, let me get this, shrink this a little bit. This resistor that lives in the rotor circuit is going to be indicative or proportional to, I shouldn't say proportional to, it has to be adaptable so that it can represent the amount of power that is output of the machine. And if you had lab yesterday, we saw that the power output varied based on the speed of operation. And one of the things we didn't get into lab, but we will get into a little bit more, is we can also equate the speed of operation to slip. So we defined that term at the beginning of last class, which is the difference between operating speed and mechanical, synchronous speed and operating speed. Excuse me. So that is the concept of slip. So what we're going to do is we're going to eventually adjust our resistor there to be a function of slip. So we did this whole work, and then we ended up substituting. So here was our final rotor equivalent circuit, where we had our resistor here, our R sub R has over a value of S, and then we substitute that back in. So we got rid of our transformer because the very difficult part, almost impossible actually, is to figure out what that turns ratio is between the rotor and the stator windings. So we oftentimes just do things as a ratio of block rotor conditions, and then we reflect everything onto the primary side. So we can accurately indicate what the model is going to respond to. So this is our equivalent circuit. Remember, this is equivalent. This is not actually in the real world, but if you put a circuit like this and you energize it with a voltage source, or preferably a three-phase voltage source, remember you have three of these, then we're going to be able to go ahead and accurately predict what the operation of this particular machine is going to look like. So then we moved on. Now we're moving on to a new, which is we've got losses, just like we did in the transformer. We have copper losses in the windings. The windings in our induction machine are stator and rotor. We have core losses, just like we did before, because of eddy currents. What's different though now is because we have rotation, we have friction and windage losses. So this is the huge divergence between mechanical systems and transformers, because our transformer doesn't rotate. So you don't have friction and windage losses. So you can see, all things being equal, our core and copper losses are going to be small, but the mechanical losses, the friction and windage losses, are actually going to be much, much higher. Okay. And there are ways to reduce that. So you can go with premium bearings. You can go with smooth rotor shafts. Those have less drag as they spin at 1800 RPM. Those make a huge difference. And I worked, this is a long time ago, but in the nuclear Navy, they have submarines. And one of the key things about submarine is being quiet, right? You don't want to be tracked. So the biggest noise signature that is on a submarine is the propulsion system moving through the water. What sound you get is not the impeller, as long as you're not going too fast, moving across the water. It's actually the vibrations that are given off because you get the shaft sitting around basically some bearings. And so that noise signature is what detects, or what you can give off the location of a submarine. And so one of the things that they were looking at doing was magnetically levitated bearings, like maglev trains. If you go to Asia, you can literally have a shaft, and it takes a fair amount of control to be able to do it, but you can center the shaft, and then you can continue to rotate it. And then at that point, you only have steam that pushes on the impeller blades. There's no mechanical contact between the hull and the shaft. So very, very quiet design. I don't know, because that was government secret work, and I don't have a government secret clearance anymore. So I don't know where that work went to. But the stuff I did wasn't government secret. It was just looking at doing some stuff. So efficiency losses are going to be pretty dramatic. So 91, 92% efficient motor is a pretty darn efficient motor. That's a premium efficiency motor. You can also buy better quality bearings. You can have more polished bearings. You can actually see how they'll actually put bearings and they'll throw them in a spinning mechanism with a really fine powder. Anybody know what like one of the finest sanding abrasives is? Yeah, well, what grip, what is it made out of? One of the
Shells
best
of like
ones.
all walnuts, right?
Well, kind of eat it. Not quite. Walnut shells. Crack the walnut shells and you got a hard surface so you can grind it down a little bit, but it's not so hard like you would with stones. And you can get them to be soft so that they can actually just run them around, and over time they will smooth things out because the bearings themselves aren't directional and the walnut shells aren't directional. So you can get very, very smooth operation. So that's how you polish or smooth bearings. If you're really into cars, you can actually do things with polishing. Anybody know what wet sanding is? What's another way to say wet sanding? Sanding with a finer grit of paper, essentially, right? You put water, it provides less friction. So when you're sanding an object, if let's say you have a 1500 grit, you put water on it, and I don't know what exactly it is, but it probably takes it to 2000 or something like that, much, much smoother. And you can add soap. There's all kinds of things if you want that. That's essentially what buffing your car does. Takes the swirl marks are. Anybody know what swirl marks are? That's the crap in the paint. It scratches in the paint. So what do? When you buff a car, you're removing paint. That's literally what you're doing. Buffing is another way to say sanding, hopefully very fine. So how's the power flow in the motor? Pretty similar to our generator. But now we're going to get a little bit different discussion because we're almost exclusively going to talk about an induction motor. And we had a senior project presentation that talked about using washing machines potentially as a source of electric power. That would only work, but most washing machines would be a single phase induction motor. You'd have to spin it at higher than synchronous speed. So it could work as a generator, but it would have to run. Remember how they talked about spinning it at 1200 RPM? That one would have to spin it above 1200 RPM to be able to get it to operate and put out some power. But here's our diagram. So very similar to synchronous generator. We're going to add one little term, and that is this air gap power, because in the synchronous machine, we had electricity that would jump across the air gap, but we still had that magnetic field coming in. In this particular machine, all the power, including the power in the rotor circuit, comes from the stator. So you actually have power that jumps across the air gap and does it really well to magnetics. Then we take off one last electrical loss. That's the rotor copper losses. And at that point, all that power, all the electrical power that has gone, is going to be subtracted out, is gone. So everything at this point forward is mechanical power. This is where you have a line of demarcation where you convert electrical power to mechanical power. So that's why it's P converted, okay? And that torque is not output torque, it is the induced torque. This is what the actual induced shaft torque is going to be. But I've still got some friction and windage losses and some miscellaneous stray losses that I can't categorize. So that's the actual output power that I'm going to see is by subtracting those last two there. So the last two are mechanical, everything else is electrical, okay? And again, the last two probably are the more dominant ones that exist there. All right, so just a summary of equations. You should be sick of that first equation by now, right? How many times have we done it, and how many times on a test has it been brought back up because we just use it so much? So that first equation is pretty darn important. It's just using square root of 3 or 3. You get to pick your choice. We use the cosine theta because we need the real power, not the reactive power. Stator copper losses, we have 3 windings with 3 equivalent resistors, 1 in each winding. So we have 3 times I squared R. Those are your stator copper losses. And then if I want to go and figure out the air gap power, I see that air gap power, I remove my stator copper losses and any core losses. If I can't get a value of R sub C, which I most likely won't, then I'm oftentimes going to try to ignore the core losses as much as I can. Okay. So my air gap is going to be equal to my P in minus my stator copper losses and whatever core losses if I can categorize them. There is no equation for that is basically what I'm saying. Rotor copper losses are the same thing, I squared times R. I've got 3 of them. And going back up, once I get into my air gap and I know what my rotor copper losses are, then I can subtract rotor copper losses from my air gap power, and that is mechanical converted power. Okay, that is P converted. And then lastly, my output power is just my converted minus my mechanical losses. And then this power is going to be equal to, and this is just a definition, power equal torque is equal to torque times omega. So my induced torque is my my converted power divided by my mechanical speed. We'll see how we can also come up with an equation for that being equal to our air gap power divided by our synchronous speed. Essentially, what you're going to see is my air gap power is going to be equal to my converted power, but I have to multiply it by 1 minus S. Okay, we'll see that in a little bit here. All right, so let's take that equivalent circuit way back over here, the R2 over S, and let's break it down into 2 parts. Let's break it down into the I squared R losses, right? Those are I squared R losses. And what is this right here? That's P out. So remember how we need to have a resistor in there that is proportional to the mechanical power demanded. It's right there. It's written as a function of slip. All I did is I took R2 over S and I broke that out into those 2 separate terms. Everybody see how that happens? Anybody want to see how that works? Okay, so I say that these 2 are equivalent to R2 over S, right? So let's add them together. R2 plus R2 times 1 minus S all over S is going to be equal to R2 times S plus R2 minus R2 times S all over S, right? Common denominator, I add them together, put them in the common denominator. Those 2 will cancel. Same thing. Okay. I just literally pulled those 2 apart because I need to know what the losses are in the machine and what the output power is going to be. So if I can develop this as a set of equations, how about doing loop equations, right? Writing a set of loop equations where perhaps I can write a loop equation that is a function of this resistor over here. Then I can go ahead and solve for all speeds. I can solve for currents, all that stuff. So what we did in lab, I can actually do that with equations. Okay. Now the question is, does this equation R2 times 1 minus S over S, does that make sense? Well, let's go at synchronous speed. What is the value of S equal to? When they're spinning at exactly the same rate of speed, what's the slip equal to? Slip is the definition of the difference in speed between synchronous speed and actual speed. When they're running at the same speed, what's the difference?
0.
So slip is 0. So in this case, what does R2 times 1 minus S over S equal? Anything divided by 0 is infinite, correct? How much current flow do I have flowing when the thing is running at synchronous speed?
None.
Pardon? At synchronous speed? Remember, we have to have a difference in speed of operation between the synchronous speed and the mechanical speed to have a dphi-dt. There has to be a difference in speed. If there's no difference in speed, there's no induced voltage or current in the winding. So current's 0. which makes perfect sense because if this is infinity, how much current is flowing through here? Not a stitch. So that checks out from the perspective of it running at synchronous speed. At synchronous speed, there's no current flow. The resistor is infinite, which means there's no current flow, which is what we expect. And what about the other extreme? When it's running at basically 0 RPM. What's the slip equal to?
1.
1. So how much power output is there? Which makes sense because if it's not rotating, power equals torque times omega. Omega is equal to 0. Anything times 0 is 0. That does not mean that torque is 0. Anybody ever tried to take a tire off their car when it's all rusted and you're pulling like a Dickens? You're putting a lot of torque on it, but it ain't spinning. So you're not doing a lot of power. You're just pulling as hard as you can, but you're actually not doing anything. So you can have torque without power. Okay. So, but does this make sense? Well, this is equal to 0, but now look at my current. Remember how I said in lab the other day, for those of you in there, and for those who are not in lab, you'll see it tomorrow. I is going to be maximum at locked or blocked rotor conditions. All I have is just this baby little resistor R2 in there to limit the current. The current just flows through like mad because this is equal to 0. So my I squared R is going to be really high, not because R is high, but because I is at its highest. So under blocked rotor conditions, you have lots of current flow and lots of heating in your rotor. And so you can't expect your rotor to last very long because your I squared R is going to be pretty brutal. Now, do you remember how I said in lab, I mean, at the beginning of class, I should say not in lab, last class, when is the fit motor running at, what is its typical speed? We looked at some nameplate stuff. If you have a 4-pole machine, what's a typical operating speed for when it puts out maximum power, or regular power, I should say, not maximum. What is that? Very close to 1800, right? I think, and we can look at those now.
So like 1785 or what my motors are.
Yeah, 1785. Let's look at some nameplates here. So let's look at a 100 horsepower machine. Oops. Okay, I just picked this one. It looked clean. So this is a baby one. This is not a good one. Let's pick a big one. This one is, doesn't say the power output. Try this one. All right, so 75 horsepower. That's not too bad. We'll say it's over here. Look at the speed. 1780 RPM. Hey, wait a minute. What's going on over here? 1470. Paul lied to us. He said it should be running at 1800 or 1200. What's going on with 1470?
50 hertz machine.
Yeah, sneaky, right? See the dual rated winding? You see 50 hertz? And at a 4-pole machine, it should be around 1500 RPM. That's pretty darn close, isn't it? But look at how close that runs to synchronous speed. If you look at this figure here, can you perhaps tell me why you want that to run as close to synchronous speed as possible? Say more. Yeah, the lower the value of slip, the higher this value is here. I goes down. So you have lower losses in your machine, the higher you get to your synchronous speed. You can't get to synchronous speed because it won't run, but that's why the machines run so darn close to synchronous speed. It's because they're at their most efficient. So the ones we have in lab, they're rated at 1670. You can say those aren't very efficient, they're garbage. But remember in lab yesterday, we were running way over full load amps for quite a period of time. And if you had a real world machine that did that for 13 or 14 seconds, it starts to burn up, gets too hot. So that's the reason why, for those of you from a professional or personal trying to understand what's going on, why these always so close to 1800 RPM, it's because that's where they're the most efficient. The higher you get, the higher the speed, the full load speed, meaning the closer it gets to synchronous speed, the more efficient that machine's going to be. And that's when you get to these premium efficiency type machines. That's what they're designed to do. You can't do too much with R2. You're kind of limited. I mean, you can do more stuff, but then you actually have a bigger shaft. It gets to be some problems. So the thing you do is run at higher speeds. Okay. Remember, I promised I would explain why they run so darn close to synchronous speed and not at half speed, because you would get a really hot motor. And that's where all the losses are in a real world motor, I squared R. I did have one application when I worked at a nuclear plant. They had wound some motors that kept burning out. These were compressor motors, and they just kept rewinding them with higher class insulation, thinking they could handle the higher temperatures, but they kept burning up. Well, the reason why they kept burning up is the core losses. So they were pushing them harder, which means they were moving more magnetic energy through, which means they were getting more eddy currents. And so they just kept burning up the cores until finally they scrapped them and ended up replacing them with much better quality, bigger motors. All right, so let's keep going with our power relations. So we did a bunch of these already, but now we're going to expand a little bit to see where maybe we can simplify. So we've already gone through these through this equation we've done. Now we're going to say, instead of going from left to right, where we take our input power and minus our stator core losses, our stator copper losses and our core losses, we could go the other direction, coming from right to left, and we can say that this is also the same thing as the converted power plus whatever rotor copper losses we have. Now, if we combine those two resistors, remember those R2 and then that R2 times 1 minus S over S, if we combine it back to this, all the power in the rotor circuit is represented by here. So that includes all the power that is converted mechanically, plus the rotor copper losses. So combining these two, we got this R2, let me get this out of the way. We got this R2 over S, all the real power loss can be identified in this location here, which means it's 3 times I squared R2 over S. If I look at this closely, 3I squared R2 looks awfully similar to something. It's the rotor copper losses. We just divided by S because we have that term there. Now we move over here to our converted power, which is our air gap, which we wrote as a function of rotor copper loss, and our actual rotor copper loss. Put those in the same equation, and we have P rotor copper loss times 1 minus S over S. Does this look familiar to you at all? This 1 minus S over S? Right here. If this is the rotor copper loss, this is I squared times R. The I squared gets square rooted. This just multiplies it out front. So we're just multiplying it by 1 minus S over S. So that's exactly what we expect. Take the rotor copper loss, multiply by 1 minus S, we have that value. Now, our converted power, when we put this under our, well, we substitute our rotor copper loss here. Do a little bit of math. Our converted loss is 1 minus S times our air gap. And again, this is important because when the slip is really low, which means it's very close to synchronous speed, almost all the air gap power is converted to mechanical power. I don't want power to be lost in the rotor circuit. I want as much of the air gap power to be converted. Then I can do something mechanically with it. Now, the downside is as I get higher synchronous, I get closer to synchronous speed, I do increase my friction and windage losses, right? Instead of running at 1700 RPM, I'm running at 1780 RPM. There's going to be more drag on the shaft and the bearings. So it's not a perfect scenario where you get something for nothing. But the general rule of thumb is if I can increase this and I don't get too much of a loss in my bearings and my windage, then I'm pretty good with it. So that's my converted power. Now my output, P converted minus friction and windage. My induced torque over here is P converted divided by omega sub n. Now I can actually see where I get that P air gap divided by omega sub s, because my converted power is 1 minus s, P air gap, and my mechanical speed is 1 minus s times my synchronous speed. So divide those out, and that's where we got that first equation. So you can make some substitutions, but more importantly, you can actually look at my equation and see, wow, that's how I'm actually getting power that's converted. And again, I want my machine to operate at low a slip as possible. So here's our relation. For 1 unit of air gap power coming in, I use slip of that percentage into rotor copper loss, and the rest is converted. So if I reduce the slip, I reduce the losses. I get more converted power. That's all that means. That's what we want to do. That's what we want to do. And that's why we also want to run variable frequency drives. Variable frequency drives, our mechanical engineering friends will say, let's run a 9.3 horsepower load. We'll run it with a 10 horsepower motor. It's going to run at a higher speed, but that pump that it's driving doesn't need more than 9.3 horsepower. So they have to design a recirc line. Well, if I could run a variable frequency drive that essentially changes the sync speed, so it's going to adjust its speed, so it's going to reduce the slip. So not only does a variable frequency drive mean you don't have to build a mechanical system that takes all that excess energy, but it also means you're going to run at a higher, more efficient motor operation because you're going to run at lower levels of slip. Okay, let's take an example. We have a 40 volt motor, 60 hertz, 50 horsepower, three-phase induction motor. It's drawing 60 amps at a 0.85 lagging power factor. You got a bunch of losses, stator copper losses, 2 kilowatts, rotor copper losses are 700, friction and windage 600, and core losses are 1800. We can neglect any stray losses. All right, so find the air gap power, converted power, output power, and motor efficiency. So this is the nameplate data. I don't care as long as it's less than 50 horsepower. The motor is rated to deliver 50 horsepower, but that's not relevant to me. It is drawing 60 amps at a 0.85 lagging power factor. So what I would start to work
question
on this problem.
for you, Paul.
Go ahead, sorry.
Yeah, that 0.85 power factor, is that like the nameplate power factor? So it's not dependent on the load or anything?
So that's a great question. So the question is that 0.85 power factor, that is dependent on the nameplate of the motor, and the answer is yes. And the reason being is the load is purely real power, right? The load doesn't consume 32 bars because that's power that has to go back to the grid. So the load is literally just real power. So that power factor is determined based on the construction of the machine. It has nothing to do with the load. As long as the load is, you might have a little bit of a change if you're not running at full output, but the nameplate rating of that motor is, if you're delivering full output, it's going to need 0.85 lagging power factor operation. So yes, that is all determined by the motor. And that's because look at those big inductors. Go back to our transformer equivalent circuit. We've got a lot of inductors. So we're stuck with it. Okay. All right, so let's go ahead and start doing our diagram. So here's our input power. Square root of 3 times 480 times 60 times 0.85, right? Because that's our power factor. So that's the actual input power. What's the next thing that drops off? We're on the stationary side of things. What's that? Well, let's start off with the stator copper losses. Pull from there. Then we're going to pull out our core losses. And at that point, this power is what jumps across the air gap. This is the power now that is converted, not converted, but transferred, if you will, from the stator part to the rotor part. Now I'm on the rotor. Now I can subtract rotor copper losses. And at that point, I have no other electrical losses to account for. So at this point, I'm converted power. Okay, this is all mechanical power. And now I need to pull out any friction and windage losses. And then this is my output power, which is my load torque times omega sub n. So the air gap power just, yes, sir. Yes. You might have stray losses at the end, but on this one it's 0, so we just left it that way. Yep. So my air gap power is my input power minus stator copper losses and core losses. My converted power losses is my air gap power minus my rotor copper losses. Oops, P rotor copper loss. My output power is going to be equal to my converted power minus my friction and windage. And then my efficiency is P out over PM. Okay. So draw the diagram at front, and then perhaps you can kind of start to see how some of the things work out. So let's go ahead and continue. Here's our input power. 42.4 kilowatts is the actual calculation. My air gap power, stator copper loss minus core, 38.6. Converted power is my air gap minus my rotor copper losses. And this is just converting it to a kilowatt. That's why you see it divided by 1,000. Or you could put 0.7, it doesn't matter. 37.9 kilowatts. My output power is my converted minus friction and windage, 37.3. And what do you know? It just so happens that it delivers 50 horsepower. But that's just coincidental. That's just a coincidence that we actually were drawing 60 amps. In reality, it's almost never. I don't think I've ever seen an application where a motor is operating at nameplate. Good question. If it's over 50 horsepower, what happens? Well, the answer is it depends. What's that? Redesign it. So let's look at that nameplate again and let's see if we can see anything interesting on it. This one doesn't have enough detail. Let's look at this one. That one we can't read. Can't read. Let's just find an easy, simple one that we can read. These are all old nameplates. Jaguar cars, look at that. Ooh. Can't see. Okay, let's take a look at this one. Doesn't have it on this one. I'll try this last one, and then if it doesn't have it, I will tell you. This one has unity power factor, which I don't. Oh, this is a generator set. That's why. So that's BS. That's not real. I don't see it here, but on most motors, you have something called the service factor, which is a multiplier. So if you buy a 100 horsepower motor, if it has a 1.15 service factor, you can actually operate that motor at 115% of 100 horsepower and it still would be okay. So it's margin.
So what is not okay? It's like,
Yeah, so and like anything, over time, when you run a motor, which too much, so there's degrees, right? So if it's slightly overloaded, it might be okay as long as it can reject enough heat to at the ambient. So a lot of times it's like it's designed for 40 degrees C ambient. So you take that motor and you put it in a room that's at 40 degrees C or what is that, 94 degrees Fahrenheit. It should be able to reject enough heat so that the insulation doesn't start to degrade. If the insulation starts to degrade, then you're going to get a short circuit. It's ultimately what happens, and you get a fire. Your motor catches on fire, essentially because you get short circuits in there. Now, the other option is if you can get better cooling. So if the room is not at 40 degrees C ambient, if it's at 10, then you can just reject more heat into the room. So as long as there's enough rejection of heat from the hot spot out into ambient, and it keeps the temperature, the hottest spot where that winding is, as long as it stays below what the insulation class is, it should run fine. Okay, but you know, that's one of those things you never want to try to push, but most motors, if you buy it for a 10 horsepower service factor 1.15, it's more likely that it's going to be running at, like I said, 9.3, 9.2 horsepower because they will run overloaded, meaning they run over their normally rated speed. What's that? They are not necessarily, the insulation is typically not heat conductive. It's usually resistant to a certain rise. So like PVC, polyvinyl chloride that you have in your house, that can do, I can't remember what the temperature is, 100 degrees C before it starts to degrade. So it's not necessarily a good with heat transfer. It's just that it can handle a certain temperature rise. The heat transfer basically has to be like you got to blow air over it and it's just got to get it cool. But you can get really fancy ones like mineral, I mean, rocks. Literally, you can take like rocks and provide good insulation. They can, I don't know how they do it, but they can compress it and it can handle extreme temperatures, 400, 500, 600 degrees Celsius, really crazy high temperatures, but you don't see those all that often. Most, I think, applications that you'll see 200, 220 degrees Celsius, I think is like probably the maximum you'll typically find. Anything above that, right? When you touch the motor, it's going to be burning hot. So you don't want people to come in contact with the motor. They could burn their hands. So typically you want it to be under boiling temperatures for any human to come into contact with it. But air, blowing lots of cold air, fans, external fans, the more cooling you can have, the better. And the best one is water. If you could run water through the windings, you could run them at much higher temperatures. But water and electricity don't always mix so well. So you don't see a lot of water cooled electrical pieces of equipment. They do exist. They certainly exist. Anybody here really into high-end computers?
I have a water cooled motor in the lab here.
You have a water cooled motor?
Yep, you can fill the whole thing with water.
You can fill the motor or you can fill the cooling.
The motor.
So it must be like a totally enclosed.
Yep, specially encapsulated windings and magnets.
Yeah. Yeah, so once water starts to get in around the windings, you can usually get yourself some problems. But he's doing submersible stuff that's actually underwater. So I would say that that's not the norm. That's probably
no. Oil filled is common though.
What's that?
Oil filled.
Oil filled is
more
oil
common.
filled motors or submersible stuff.
Yeah, all of our submersible stuff are always oil filled, generally speaking.
Yeah,
you can have that go
electrical
through your
equipment
coils.
has got oil for insulation for transformers and stuff, but you don't see a lot of motors doing that again, unless it's a submersible application, which means you
To keep
can't,
water
it's
out.
going to be underwater, so you got to have a certain pressure. So they put oil in, they bolt it up, and then they just stick it underwater. So, and then the oil, the nice thing about the oil is you can circulate it through. So you can run it to radiators to cool it off. It's not like the dry type insulation that you typically find. So service factor, and I don't see this on that nameplate. Usually that's a pretty common one that you'll see, but I don't see that here. Efficiency, 88%. It's pretty darn good. Not bad. Not great, but not bad. Which is probably like the theoretical, getting close to the theoretical limit if you're talking about EVs in their motors, 92, 93% efficient. It's probably, you know, the typical newer technology motors that you're finding. Which sounds like crap, but keep in mind, how does your reciprocating engine do?
15 to 30.
Gas engine's probably 25, 27% efficiency. Converting fuel to actually power to the wheels. What's that? They make cool noises. Well, I can put speakers on a car if you really need the noises, right? Yeah. Well, you know, the idea is, and you also, you can't cheat too, because if I have an electric vehicle, I also have to include the inefficiencies of charging the motor, I mean, the battery, right? Because I have an external charger that has, you know, that could be 90% efficient, plus whatever the losses in the converter are. So you're probably talking converter and everything efficiencies 60 to 70%, which is still twice what it is for a reciprocating engine. So reciprocating engine, it's not a knock on it. It's just limited by the theoretical Carnot efficiency, right? Carnot says, here's the theoretical limit. You'll never exceed this efficiency. And if you look at the two temperature differences, it's not a huge difference. Inside of an engine, 400 degrees, 500 degrees. Outside is 80 degrees. That's going to limit your theoretical value. So that's why you see people adding turbos and intercooling and all this stuff to make it more efficient, which it does, but you can't, you know, there's only so many things you can do.
Well, I don't know if you saw Mazda's new hybrid vehicle where it runs a rotary engine at a constant RPM to charge a generator, which then is it's an all electric car from there on out. So they're quite efficient. I think they have like a 100 miles to gallon range or something like that, which is insane for, you know.
Say that again. I'm having a really hard time hearing you.
Sorry, is it better? Can you hear me?
Keep speaking. It's like it's really hard to hear.
Let me turn up my
There you go.
input
We
volume.
got you.
Okay. Yeah, I was gonna say Mazda just come out with a rotary engine that, you know, because it runs at a constant RPM to power a generator is, you know, a little bit more efficient than having to vary RPM with load. And then it charges the batteries on the car, which then it's fully, so it's like a diesel electric, but it's not. It's like 100 miles to the gallon, which is insane. Yeah.
Hybrid vehicles have come a long way, but you still have that energy that you can store. That's what the batteries really make their money, is they do regenerative braking. All that energy that would be lost in terms of friction gets converted to stored energy, and then you can reuse it. So
I know about.
battery,
I know about the big problem. I never understood how the
there's no friction from the brakes. You remember how we take a motor and we put power in, electrical power in to get it to spin a magnetic field, and they chase each other? If you alternate the direction, you can make that brake act as a generator. So when you apply your foot on the brake just slightly, your brake pads don't squeeze. It actually causes a magnetic field to rotate backward, and you take energy out, mechanical energy, and because now you have magnetic fields chasing each other in the opposite direction, it will slow the vehicle down. So regenerative braking is your motors that are driving your wheels operating as generators. They're recharging the battery. They do. Yeah, you still need brake pads because you can only charge and discharge so much. I mean, theoretically, you can make it powerful enough that you could lock up the wheels, but they still put friction brake pads on them. Yeah, you can get many miles on hybrid vehicles because as long as you're not jumping on the brake pads all the time, you don't need much. Yeah, semi trucks use engine braking, which is now becoming more illegal because of all the noise it makes. Cool noises at 3 a.m. when you're dead asleep and your 6-month-old is dead asleep in the room next to you.
Paul, I added a nameplate of a motor I have here in the lab. It's got the service factor you were talking about.
Ah, so Nate was kind enough to share.
Should be in the chat.
Let's see. So Nate was kind enough to share. Can everybody see that? Whoops.
Yep,
So this
that's-
is, oh, of course, Euro Dry. That's European stuff is pretty cool. But you can see here, service factor 1.15, totally enclosed, fan cooled. Nominal efficiency 95%, which is really, this must be a pretty darn expensive motor.
Yep, it's got a gearbox on it too, so
That includes the gearbox efficiency?
no, not a
Okay.
chance.
I was gonna say, if you're getting 95% with a gearbox, then
Yeah,
I'm
it's got
doing my
a,
job and I'm just gonna sell these on the street because these
That-
things are gonna make a killing.
that's a 30-to-1 gearbox, so yeah, there's a lot of efficiency losses there.
But look at the power factor, 0.85. Pretty typical.
And inverter duty.
Yeah, inverter duty means that you have variable frequency drives and they put out waveforms that aren't perfect. So you get harmonics, which can make the waveforms choppy, which can affect the insulation, but it also can affect the neutral, although this one is all delta connected. So I don't know what the concern would be, but we'll learn about KVA code and NEMA design here. This stuff will make a little sense when we get further along. This NEMA design is basically the characteristic, the torque versus speed characteristics. This KVA code is how much it costs to start. In senior project presentation, they were talking about cold load pickup. It's kind of the same idea. It just tells you how much power it draws. Yeah. Very fancy motor, 95%, totally enclosed, fan cool. Most of the ones I've seen are ODP, open drip proof, which literally you can see on each end. And drip proof just means it has a case on the top. The water is dripping. It should not go into the windings. But if you spray a hose on it, then you get water in the winding. This totally enclosed fan cool, you can spray water in all directions and you can still not get water on it. But it has to be much upsized because it has a lot of heat and it doesn't reject heat as easily as the open drip proof.
That's a $12,000 motor with a gearbox.
What's that?
That's $12,000 with the gearbox.
$12,000 with a gearbox, and it's only, where's the horsepower on it?
It's 60 horsepower.
60 horsepower? Yeah.
Yep.
It's a pretty expensive motor. Okay. Any questions on this stuff before we move on to the next little bit? And I did put this stuff up here. All right, let's keep going. Okay, so we'll go back and do some circuit analysis. So again, we have all this relevant stuff, 460 volt, 25 horsepower, 60 hertz, 4-pole, yada, 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 a lot of information. Now we have a lot of data here, which means we should be able to build an equivalent circuit of our motor. Okay. And why are we doing that? Because I don't know what the current is. I is a question mark. So I need to start drawing an equivalent circuit to be able to get this thing to do that. So let me bring up whiteboard. And we'll draw the equivalent circuit. And then we'll fill in the blanks when we're ready. Okay. So we're going to put our base elements in here. Whoops. Resistor, an inductor. We'll put an inductor in here, another inductor, and another resistor. And we'll put this one over here. Whoops. just in case, but we can always treat it. This is X2, XM. Don't forget, these are J terms, JX1 and R1, not R2. Okay, so this is our equivalent circuit of our induction machine. Now we're going to go ahead and start filling in some parameters. So I'm going to use my snipping tool and snip this data over. And put in these values over here. All right, so this is 0.641. This is 1.106 J. This is 0.464 J. This is 0.332. This is 0.332. And again, we can combine those. We just don't know the slip yet. And then XM is 26.3, J 26.3. So now I'm going to delete that and zoom in here. All right, so we have almost our whole circuit done up. Now we need to go ahead and take a look. It's 460 volt. So the voltage over here is 460. Got to convert that to a phase voltage. That's the voltage that we apply. Now we have enough information to answer the question. So the first thing we need to do is speed. How do we calculate speed? Well, it's a 4-pole machine, which tells us that our synchronous speed, hopefully we can feel pretty comfortable about just writing that down. That's 1800 RPM. 4-pole machine tells us synchronous speed is 1800 RPM. To find the mechanical speed of operation, it's 1 minus S times our synchronous speed. Now to figure everything else out at this point, we need to convert this to our equivalent circuit diagram and start to do some calculations, okay? So we can figure out speed, but everything else, we're gonna have to go ahead and do that. So we're gonna go back to our diagram. And I'm gonna clean it up a little bit and then just write it as a bunch of values. R1, JX1, JXM, JX2, and then I'm going to combine these two into R2 over S. Now, I'm ready to do circuit analysis. So I have positive V is equal to remember that? Anybody not see how I got that? Anybody see how I got that? Mesh. Whenever you're in series, it's always better to do mesh. Does everybody want to see me write it out? Would that be better?
Yeah, probably once more
Okay. So
refresher.
I1, I2, right? We typically start over there. We'll put our voltage drops in this direction that we have shown. Okay, mesh, we feel pretty comfortable with what we've got there. So now we're going to go ahead and do our equations. As the sum of voltage drops is equal to 0, negative V plus I1 R1 plus I1 JX1 plus I1 JXM minus I2 JXM is going to equal 0. We're on that closed loop. That's writing it out full Monty, not trying to add, subtract. And then the bottom one over here, we have negative I1 JXM plus I2 times JXM plus I2 times JX2 plus I2 times R2 over S equals 0. Now I'm going to make these go into standard form with my voltages on one side and then my currents on the other, and then I'm going to sum them together. I've got an I1, an I1, and an I1. So that's going to be minus or plus, sorry, equals. That equals I1 times R1 plus JX1 plus JXM minus I2 times JXM. That's our first equation. Our second equation, there's nothing on the left-hand side. There's no voltages. That's equal to minus I1 JXM plus I2 times JXM plus JX2 plus R2 over S. And then I just put it in matrix form so that I'm right over here. Okay. Is that better? Go through that slower? Easier to follow? Now, does anybody have any heartburn with doing this? If you've had 324 and 325 with me, I'm hoping you're fairly comfortable with this. If you hadn't had me in 324 and 325, depending on how you were taught circuits, you may not have had a lot of linear algebra. But linear algebra will save your butts, because if I had to solve this equation for I1 or I2 and substitute in the first equation, that's a pain in the keister, right? But if you use algebra, linear algebra, it's much easier, because now I can solve for I1 and I2. It's going to be equal to R1 plus J X1 plus XM minus JXM minus JXM R2 over S plus J times X2 plus XM. That whole thing inverted times my voltage matrix, which is V and 0. So now here's the thing. If you're comfortable with MATLAB, you can just write this as a script file, and you can write it as variables. R1, X1, XM, blah, 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 blah. You don't have to do this every time. You can just use your script file. Or you can plug it in your calculator. You might be able to do it in your calculator. I think that's what I've got here. Here's my voltage. 460 divided square root of 3 at an angle of 0. I gave you my N sub S, N sub M. Look at my Z matrix. Pause for station identification. Isn't that our Z matrix we just developed? So I entered in my values here, including my voltage, and if I needed to, my number of poles and my frequency, and then everything else up to efficiency, which is really what I want to get, is going to be determined from here. So all this is where this is just a copy job. This is what I enter. I guess technically I would enter up to here, but everything else is just calculations. So if I run it to here, so I set my breakpoint, and I run it. Now I go back to MATLAB, which is, and there's my data. Speed 1746 RPM. My stator current is 22.86 at an angle of minus 28.65. Where did I get I1 from? Here, I pulled I1 out of that matrix. My stator current is the current flow. Here, this is I1. That's my stator current. Isn't that the current going into the stator? So that's that current that I pulled out right there. See, it says I stator equals I of 1. And then I just make a sexy display. So I show magnitude and angle. Then I have my input power. And then I don't remember why I did this. I have to check. My power factor of my stator, my converted power, my output, I'm not sure, I must have a typo where I did that twice. My output power, my induced torque, my load torque, and my efficiency. I'll show you here in MATLAB, here, so we'll see it all here, the actual calculations, and then we'll bring it up in MATLAB. And I'll give you lots of time to ask questions, because I promised that I wouldn't do it, but here's our speed. Here's my Z2. So this is doing things and doing it in terms of series parallel combinations. So you see Z2 and then my ZF, which is my JXM in parallel with my Z2. So I had to do this equation. Then I had to put in parallel to come up with this. Now my total is going to be the, yes, sir? Sync speed? No.
No.
Yes, 2.2%. That was given. But the total impedance, I have to add that to R1 plus JX1. So look at all the work that I needed to do just to get this equivalent input impedance. Now I can calculate my current. Oh, why is the current up a little bit? Do I have the correct values? Let me look. Let me just double check. Let's see, 0.641. Oh, slip is off. That's why. Sorry, guys. It's 0.22, right? So let me run it again. Let's go back to our current. 18.89 at an angle of minus 33.69. Isn't that the exact same value? Nothing up my sleeves, no tricks here, right? This is MATLAB. I'm not pulling any wool over anybody's eyes. Go all the way to the beginning, clear CLC. What does that do? It clears the screen and all the variables. So every time you see this, you got to know that Paul's not just playing, smoke and mirrors, because this clears all the variables. So when I ran it here with the correct slip of 2.2%, I ended up getting that a current. And all I had to do was enter the matrix. So there's a little bit of setup, but I feel like this is a little less stressful than, okay, now I got to look at the circuit and I got to do a parallel combination, then a series combination, then another series combination. It's like, no, I don't need to do that. I can just, do brute force. Up to you, your choice if you want to do it that way. So here is my stator current, my power factor, 0.833. Just take the cosine of that angle. It's lagging because of the negative. My voltage is at 0. My current is at minus. My input power, 12,530. Before I switch pages, let's go back to here and let's see how close I got. So here's the power factor. I said 0.833, 0.832. I mean, it's rounding a little bit, I would imagine. My converted power, my input power is 12.53. I don't actually calculate input. Oh, here it is, 12.525. So that's almost exactly the same. Keep going. Stator copper losses. So my air gap power is 11,845, which if I look at my air gap power, that's converted. Do not calculate air gap power. I guess I didn't calculate the air gap power. I guess I didn't include the air gap power. Let's add that in. We can show you how quickly that is to add in. So my air gap power, I'm going to put it in right over here. Oh, I did a comparison. That's what I did. Sorry about that. So remember I said, let's do the brute force method, which is the actual approach, or you can do the other approach, which is just doing the comparison. This is at R2 times 1 minus slip over SIP, and we get the same result. So my air gap power is equal to my converted power minus my rotor copper losses. So let's see, do I calculate rotor copper losses? No, my rotor copper losses are right here. So I will copy that over. So 3 times I absolute rotor copper loss. I even called I2, I called it I rotor to make it easier. Notice I took the absolute value because when you do I squared R, it's the magnitude of I, not I, but the magnitude of I squared times R2. So let's rerun that. And here's my air gap, 11,318. No, wait a minute. Am I subtracting the wrong one? Oh, no. Yep, this is the wrong one. This is going to be, it's going to be P in minus P air gap. Yeah, because converted power is mechanical to electrical. So try that again. 1184.5 versus my air gap. Why am I having a hard time with this? This is like not. Oh, geez. Air gap, the pure air gap is not stator, it's not rotor, it is I stator times R1. Right? So this right here is the air gap power. We'll get it right at some point. So 11.8, what was it? 845 versus 11,839. Again, it's off by 6 when you're comparing almost 12,000 watts. So pretty good. Okay. So that looks like it's the right value. Now I'm going to continue. My output power is going to be equal to 10,485. I look over here, output power 10,478 versus 10,485. So again, off by 7 watts. Now my induced torque, air gap power divided by my omega sync. It's also, that's my induced torque. Then my load is going to be my output power divided by omega sub m. My induced torque, we can look at the equation here in a second, but I've got my air gap. So this is 62.81, 62.8. And then my induced torque, 56.84 versus 56.9. Then my efficiency is 83.7%. So going back to the script file, remember, this is all, and I'm going to move this down a little bit. So I'm going to put this as input data. And then everything over here, calculations. And all these equations here, up until where that line 38 is, that's all just equations. So the only thing differently that I did between the slides and here is I directly calculated I1 and I2. That's a little bit better because if you go over here, if I need to calculate rotor copper loss and any of this stuff, I have I1 times R1. Why did I have to go ahead and do the converted power when I use my 1 minus S? Because I don't have the value for I2. So I need to use this equation to do the calculation. But if I know what the rotor current is, I can directly pull that out, which is what I did right here. See the converted power? remove my stator copper losses and my rotor copper losses to get that equation. So up to you how you want to do that. Questions on doing the calculations? Yes, sir.
Kind of, how long is that?
10 minutes? What's tricky about it?
It's all pretty straightforward, but.
Well, it's a great point. It's when to use what? Everything in here is entering your data in your calculator, right? P rotational, all these would be writing it on a piece of paper and then putting those variable names. Once you get to here is when you do the calculations. That's the power of MATLAB. I put all my variables in here and it calculates it for me. You have to do that on your calculator, but these steps right here, these are calculator steps. And to solve for this impedance network, you could either do the series parallel combinations, or you can just use KVL and loop equations, and you can pull that value out. So everything here, if you look at it, is multiply, divide. Now, I did get a little cute here when I was trying to display this current, but that's just because MATLAB doesn't do a very good job of displaying data. It always does it in rectangular coordinates. Your calculator, you can switch modes. But everything else, right? Like even over here, I figured out S equals 3 times VI conjugate, right? That's an equation you have to put in your calculator. And then if I wrote it in rectangular coordinates, I would just write the real part. So I display that as the real of my input power. That just makes it easier to display. It actually is solved for in this equation. This is, again, is just a display parameter. So a lot of what you got to do in MATLAB is not the calculations that, I mean, doing the calculations is hard in and of itself, but that's, you got to do that with your calculator anyway. This is just displaying it so that it looks and you can pull out the right data. Tell you what, I'll upload this MATLAB file so you can play with it. You don't have to write it. It's one of those things I'll put on MATLAB scripts and you can ignore it or you can use it. Totally up to you. Don't worry about what's after line 38. We'll reveal that at a later date and time. I just wanted to give you how to do the calculations. But this is when you use the tools, right? Because again, MATLAB, this is just a calculator. All I've done so far is treat it as a calculator. And I love it because this, remember, I was a student once too, and I used to get so frustrated when I would check, professor's work and the calculations just magically, and you'd ask the professor, how'd you get that number? And they would throw you out of their office because you questioned their work. Well, question me on this one. This is MATLAB. It's like you can run through it yourself and you can get the same results in the slides. So you can't say, because, that's a good thing to check, which is, hey, can I get the same results that the teacher got? Well, you can actually see in MATLAB, you don't actually have to do those steps manually. You can check to see, is the implementation correct, your own work. But I will make that uploaded after class. Okay. Sure. Questions? No questions? Okay, no questions. I will see some of you tomorrow and the rest of you on Thursday. And like I said, this week I'm wearing masks, so you're welcome to come to the live class, but I'm just doing this as a precaution for you all. So if you can't hear me, I apologize. All right, take care.